By the late 1970s, both superpowers relied on early warning systems designed to detect incoming nuclear missile attacks. These systems were composed of radars, satellites, computers, and command and control links. The doctrine guiding them was launch on warning. Low. Low assumed that if a credible attack was detected, forces should be prepared to respond before incoming weapons struck. This doctrine traded certainty for speed. Speed reduced reaction time at the cost of increased misinterpretation risk. NORAD, North American Aerospace Defense Command, was one of the key early warning institutions in the U.S. strategic system. Its mission was to provide continuous monitoring of North American airspace and missile attack indicators. NORAD integrated data from radar networks and the newly operational Overhead Early Warning (OEW) satellites. These OEW satellites were designed to detect the infrared signature of missile boosters shortly after launch. The system produced data feeds that went into automated displays at command posts. Human analysts then interpreted those feeds for seriousness and credibility. In parallel, the Strategic Air Command, SAC, maintained the U.S. bomber and missile forces. SAC forces were kept on alert according to established readiness procedures. Alert posture was not static. It could be raised in response to perceived increases in threat levels. Alert posture dictated how quickly forces would be able to take the field or execute orders. Under high alert, SAC units flew quick reaction alert missions and pre-targeted assignments. The U.S. National Command Authorities, the President, the Secretary of Defense, and designated successors, had the legal authority to order nuclear release, but decision-making depended on timely and accurate information from NORAD, SAC, and intelligence agencies. The system assumed that warning systems would produce reliable indicators of real attack. That assumption was stressed whenever anomalies appeared in sensors or reports. In 1979, the United States and the Soviet Union remained locked in protracted nuclear competition. The Cold War had moved beyond proxy conflicts to technological dominance in strategic systems. Mutual Assured Destruction, MAD, was the prevailing deterrence logic. MAD assumed both sides had secure second strike capability. The implication was that neither side would rationally initiate a first strike knowing retaliation was assured. But MAD also depended on accurate detection. False warnings could threaten that balance by forcing decisions on incomplete information. This was the strategic context in which early warning systems operated. Technical complexity, systems with many sensors and nodes, compressed timeframes, need to act quickly or lose advantage organizational incentives, avoid missed detection, even at cost of false alarms. Doctrinal assumptions, worst-case reasoning shaped interpretation. The specific incident that year began in late November 1979. At that time, NORAD's Strategic Warning Center received data that at first glance appeared to indicate a massive missile attack. The raw material feeding the warning displays included signals from missile warning radars and satellite feeds. These signals suddenly showed unexpected behavior. Because of the design of processing systems, unexpected behavior can produce alerts. Alerts are not confirmed attacks. They are indications that require assessment. In NORAD's procedural logic, the workflow went from automated detection to display, to analyst review, to recommendation, to higher authorities. This pipeline was calibrated for speed. When missiles were thought to be incoming, there was little time to delay action. In Soviet doctrine, similar processes were happening on the other side. At the highest levels, U.S. authorities depended on NORAD and SAC to filter out spurious data. They assumed that the warning network was robust enough to preclude major errors. This assumption was grounded in prior testing and layers of verification. Yet the system's operational tempo, the frequency and intensity of alerts, tests, and real data was high. A high tempo increases the chance that test signals, sensor glitches, and real signals will interact unpredictably. The structural danger, then, was that a warning system optimized for early detection and speed could produce a credible alert that did not correspond to actual enemy action. If human decision-makers treated that alert as credible, they might initiate alert actions, such as raising SAC posture or putting forces on higher readiness. These actions themselves could be observed by external intelligence or misinterpreted as preparatory moves for use. This is the structural problem at the heart of early warning systems. The system assumed it could see attack indicators reliably, but could not see enemy intent or confirm reality instantly. The incident that unfolded in 1979 exposed this structural vulnerability. It began with an apparent anomaly in the warning feeds. Understanding what happened next requires examining the system's doctrine and incentives shaping responses. Warning systems do not operate in isolation. They are embedded in doctrine and institutional incentives that shape how signals become action. The mechanism of early warning is a network of sensors feeding data into command posts. This network assumes that faster indication reduces strategic surprise. It is a procedural assumption, not a psychological one. Systems are optimized to reduce time to alert, not time to verification. In the U.S. strategic architecture, two systems were most central in late 1979, NORAD's radar and satellite detection streams. Strategic Air Command's alert posture and response protocols. NORAD's mission was defined in operational manuals. It was to provide continuous surveillance of aerospace threats and timely warning of missile attack. NORAD integrated data from early warning radars in Alaska, Greenland, and Canada. It also ingested infrared data from overhead early warning, OEW, satellites. These satellites were designed to detect the heat signatures of missile boosters shortly after launch. The core mechanism here is a data fusion process. Multiple sensors produce raw data. This data is routed to screens in command centers. Analysts interpret patterns, such as multiple simultaneous heat flashes in different geographic quadrants, as potential missile launches. The doctrine behind this architecture was influenced by the threat environment. Missile flight times from the Soviet Union to North America were short, 20 to 30 minutes. If strategic warning systems did not detect attack swiftly, presidential decision time would collapse. Thus, the doctrine emphasized quickest possible detection, even at the cost of interpretation uncertainty. This doctrine existed because of technological constraints and the physics of missile flight. Neither side could afford to wait for full confirmation before acting. That is why launch on warning doctrine emerged, not because of emotion, but because the time windows were structurally compressed. Strategic Air Command, SAC, operated under its own set of procedures. SAC maintained bomber and ACBM forces in alert conditions. Alert condition levels determined how fast forces could launch or reposition. These levels were coded, from normal readiness to heightened alert. Changes in alert level were observable within U.S. military networks, and importantly, by foreign intelligence. The institutional incentive in warning systems was clear: avoid the missed detection. A missed detection, failing to see an attack that is real, was judged far worse than a false alarm. This asymmetric penalty is embedded in operating procedures and training manuals. Analysts and commanders were trained not to ignore potential indicators. This asymmetric incentive shapes organizational behavior. It means that sensors and analysts are biased toward alert rather than dismissal. Systems, by design, prefer caution. Another institutional layer was the national command authorities who could escalate alert postures. The President and Secretary of Defense were at the top of a chain that included NORAD and SAC, but before they would act, they relied on analyst recommendations from these lower echelons. The recommendation process assumed that warning center assessments were dependable. This institutional assumption mattered. It meant that analysts' interpretations could shape national posture decisions. Humans were not replaced by machines. They were amplifiers of what the machine feeds them. On the Soviet side of the Cold War, similar doctrines operated. Soviet Air Defense Forces, PV-Ostrany, and the Strategic Rocket Forces, RVSN, had their own early warning and readiness doctrines. Their interpretations also emphasized worst-case correlation of indicators. This means that if their systems generated a cluster of signals, the Soviet structure assumed high-risk potential and consulted senior leadership. This symmetrical doctrinal structure increased bilateral risk. Both sides had systems that assumed danger until proven otherwise. Neither had systems optimized for verification before reaction within the compressed timelines. Incentives inside the U.S. military further shaped behavior. Commanders and analysts were evaluated on avoidance of strategic surprise. This meant systems and personnel were rewarded for raising alerts, not reducing them. This is a crucial structural point. People are not acting emotionally. They are acting within institutional rules that measure success by early detection, not by correctness. The technological layer also mattered. NORAD's radar and satellite systems were new and complex. Complexity introduces more pathways for error. A sensor glitch here, a timing mismatch there. Combined with human interpretation, these glitches can produce credible appearing indications. Another incentive factor was testing itself. Systems were regularly tested to ensure functionality. These tests injected test data into the network because procedural safeguards were imperfect. If the system cannot fully separate test signals from real signals, then it is vulnerable to misclassification. All these systems, doctrines, and incentives created a structural environment where warning signals could be overinterpreted. High operational tempo increased the chance that routine events, such as system tests or maintenance operations, could interact with warning networks in ways that looked like real indicators. The result: a system that assumed real threat until disproven. This set the stage for the November 1979 false warning and the alert actions that followed. The 1979 NORAD incident is best understood as a warning system failure, not an intelligence failure. The system did not misread Soviet intentions. It misprocessed its own data. The early warning pipeline had 3 stages. 1. Sensor input. 2. Computerized processing and display. 3. Human assessment and escalation. Each stage existed to reduce the chance of surprise, but each stage also introduced failure pathways. In late November 1979, NORAD's warning displays began showing what appeared to be a large-scale Soviet missile launch. The warning indicators suggested hundreds of missiles in flight. This was not a small anomaly. It was the kind of pattern that the system treated as catastrophic if true. The key mechanism was not radar detection of physical missiles. It was computerized data entering the warning system in a form that looked like real attack data. This is where the structural vulnerability appears. Early warning systems in this era relied on integrated computer networks. NORAD and associated command centers used computerized models to translate sensor input into attack assessment displays. These displays were designed for rapid comprehension under time pressure. They simplified complex data into clear threat pictures. That simplification was necessary. It was also dangerous. A simplified display can conceal uncertainty. It can make low-confidence signals look high-confidence. And it can make simulated or corrupted data look operationally real. In the 1979 incident, a training or test tape was reportedly introduced into the operational warning system. The system treated the tape's data as if it were real sensor output. This produced an attack scenario on screens that looked plausible within the system's logic. This is the critical technical failure. The system could not reliably separate exercise input from real input. The warning center's first task was cross-checking. If an attack is real, multiple independent sensors should confirm it. So analysts checked other streams: ground-based early warning radars, satellite warning indicators, secondary tracking systems. These checks mattered because they provided the only stabilizing force in the process: redundancy. But redundancy only works if the organization has time to use it, and in missile warning, time is the scarcest resource. The procedural response chain then moved into alert actions. Strategic Air Command was notified. SAC procedures required readiness measures when warning was credible enough to be treated as possible real attack. This is the central risk pathway: error to alert action. Once SAC begins readiness actions, the system's output becomes real, even if the input was false. This is why false warnings are not harmless. They activate real mobilization. The U.S. National Command Authorities were also drawn into the process. The system was designed so that top decision-makers would be notified early. The goal was to preserve decision time. But early notification also creates a new risk. It forces leaders to engage with a potential nuclear crisis before verification is complete. This is the structural danger of launch warning logic. The system pushes decision-makers into crisis posture before certainty exists. Human judgment entered at 2 points. First, analysts assessed whether the warning display matched real sensor confirmation. Second, commanders decided whether to initiate alert actions. The intersection of human judgment and automation is crucial here. Automation created the threat picture. Humans decided whether the picture was credible enough to act on. In 1979, the system moved far enough that real alert actions occurred, but it did not proceed to final nuclear release procedures. This suggests that the verification layers did function, eventually. The incident also highlights a subtle warning system weakness. When a computer-generated scenario looks internally consistent, it can be hard to disprove quickly. It fits the Doctrine's expectations, and it triggers the same procedural pathways as a real event. This is why computerized warning systems can produce severe false alarms. They can generate high-coherence threat pictures from incorrect inputs. A final intelligence factor is what the Soviet Union could observe. The USSR did not see the false warning display. It could only observe external U.S. readiness signals. If U.S. readiness actions were visible to Soviet intelligence, the Soviets could misread them as preparations. This is the second stage risk: false warning to U.S. mobilization to Soviet misinterpretation. Even if the Soviets did not observe the event directly, the possibility of observation is structurally destabilizing. So the warning system problem is not only internal, it is interactive. The incident shows how strategic systems can generate crisis behavior from internal error. It was not a case of misreading the adversary. It was a case of the system misreading itself. The failure point in the 1979 NORAD incident was not the computer made a mistake. The failure point was that the system allowed test data to be interpreted as operational reality. This is a structural category error. It is the nuclear warning equivalent of a fire alarm system that cannot distinguish drills from smoke. The mechanism was simple. A training or test input entered the operational pipeline. The operational displays then generated a coherent attack picture. That picture activated the institutional response chain. The danger did not come from the tape itself. It came from the system's assumptions about the tape. Early warning architecture assumed that the operational pipeline contained only real-world sensor data. That assumption was foundational. If it fails, the entire warning logic collapses. This is the first structural risk. Systems can be correct in logic, but wrong in input. Once the display showed a large Soviet missile launch, the system's incentives pushed toward rapid action. Because the cost of missing a real strike was existential, procedures were biased toward mobilization. This is the second structural risk. Doctrine converts uncertain warning into real readiness. In other words, the system is designed to behave as if danger is real until disproven. The third structural risk was time compression. Missile warning timelines are measured in minutes. Even if verification procedures exist, they must operate fast enough to matter. This forces institutions to run parallel tracks, verify the warning, prepare forces anyway. This parallel processing is rational. It is also destabilizing. because the preparation track produces real-world signals. For example, SAC bomber crews can be brought to immediate readiness. Command posts can shift to higher communication security. Airborne command and assets can be readied. ICBM crews can move into higher alert routines. Even if the warning is later disproven, the actions occurred. The fourth structural risk was adversary observation. The Soviet Union had intelligence capabilities to monitor U.S. strategic posture. This included SIGINT collection, monitoring of U.S. command communications, and observation of certain military movements. So even a short-lived U.S. readiness surge could create external ambiguity. The Soviets would not know it was triggered by a false warning. They would only see increased U.S. alert behavior. This is the most dangerous pathway in nuclear systems: internal error to external, signal to adversary response. The fifth structural risk was feedback loops. If the USSR observed U.S. readiness actions and interpreted them as preparations, it could increase its own readiness. That Soviet readiness increase could then be detected by U.S. intelligence. The U.S. could interpret that as confirmation of attack risk. This is how false alarms can become real crises. It is a system interaction problem. The incident also exposed an institutional vulnerability in command and control. The warning system's credibility was tied to how realistic the display looked. A coherent display can create urgency even before confirmation. Humans are trained to respond to coherent threat pictures. This is especially true when the picture matches doctrinal expectations. A large-scale Soviet strike was exactly the scenario the system was designed to detect. So when the display showed it, procedures treated it as plausible. This is not a psychological flaw. It is procedural design. The system assumed that if the warning display shows a massive launch, it is safer to mobilize than to hesitate. The failure point, therefore, was not one individual. It was the interaction of imperfect separation of test and operational data, doctrine that rewards rapid readiness, institutional incentives against missed warning, compressed timelines, the possibility of adversary observation. The system produced risk because it could not guarantee that its own inputs were real. That is the defining vulnerability of computerized early warning in the late Cold War. The question then becomes, once the warning moved into alert actions, how did the decision chain avoid escalation? Once the warning display generated an apparent large-scale missile attack, the U.S. system shifted into its crisis workflow. This workflow was designed to preserve retaliation capability while verification continued. The key point is that nuclear decision chains are built with layers. Not all layers authorize nuclear use. Many layers authorize readiness actions. This distinction is why escalation was avoided. The U.S. chain began at the warning centers. NORAD's warning staff detected the apparent launch picture. They initiated immediate notification procedures. Notification did not mean confirmation. It meant the system treated the event as potentially real until disproven. From NORAD, the warning moved to higher-level command nodes. This included the National Military Command Center, NMCC, in the Pentagon and other strategic command links. The NMCC served as the central hub for transmitting strategic warnings to national command authorities. At the same time, Strategic Air Command was informed. SAC's role was operational. Its procedures were designed to ensure survivability of bombers and command systems if an attack was imminent. SAC could execute readiness actions rapidly because its forces were already structured for it. Bombers were kept on alert. Crews were trained for immediate launch. Command posts maintained continuity of command procedures. So the decision chain did what it was designed to do. It activated readiness measures before full confirmation. This is the core Cold War logic. Prepare first, verify in parallel. But the system also had verification gates. The most important gate was sensor cross-checking. If an actual Soviet ICBM launch occurred, multiple independent systems should detect it. In the 1979 incident, the warning display suggested a massive strike, but other independent sources did not confirm it. Ground-based early warning radars, did not show incoming missile objects. Satellite warning data did not match a real booster launch pattern. Other tracking systems did not support the hundreds of missiles display. These contradictions mattered. They gave the system a path to halt escalation. This is why redundancy is stabilizing. Redundancy creates multiple independent failure barriers. Another stabilizing factor was that readiness actions were reversible. Launching bombers is not the same as launching missiles. Raising alert levels is not the same as ordering nuclear release. This matters because it creates a buffer zone. The U.S. system had a structured escalation ladder: warning notification, readiness posture, increase, possible bomber dispersal/launch, higher level command relocation, nuclear release, authorization. The 1979 incident moved into the early steps, but it did not move into the final ones. The reason is that the final steps require political authorization. They also require stronger confirmation. Presidential nuclear decision-making depends on credible confirmation of attack. The system is designed to avoid firing based on a single sensor stream. This is not because the system is cautious. It is because launching nuclear weapons on false warning is an irreversible catastrophe. So while the warning system was fast, the final authorization barrier was slower and higher. Human judgment intersected with automation here. The computer display produced the crisis picture. Humans compared it against independent sensors. Humans also assessed plausibility. In this incident, human verification did not immediately stop the readiness process, but it prevented the system from escalating further once contradictions appeared. This is a key point for analysis. Humans did not save the day through intuition. They saved it through procedural cross-checking. The system avoided escalation because independent sensors contradicted the attack picture. Readiness actions were reversible at early steps. Final authorization required political confirmation. The chain contained gates that demanded multi-source verification. But the incident still produced real alert actions. This means the system reached the point where external signals could have been generated. And that is why this incident is strategically important. The danger was not only internal, it was interactive. If the Soviet Union had detected U.S. readiness actions, it could have interpreted them as preparations. That could have triggered Soviet readiness increases, and that could have produced a feedback loop. Escalation was avoided partly because the event was corrected quickly. The false warning was identified and terminated before prolonged mobilization occurred. Time was a stabilizer here. Short duration reduced external visibility. Short duration reduced the chance of adversary reaction. But the system's stability was conditional. It depended on multiple safeguards holding simultaneously under extreme time pressure. This is not robust stability. It is fragile stability. There is little disagreement about the core facts of the 1979 NORAD false warning. A false attack picture appeared in U.S. early warning systems. Alert actions were initiated. The warning was later disproven through cross-checking. The system returned to normal. The disagreement is about what the incident reveals about nuclear stability. One debate concerns the adequacy of procedural safeguards. Some analysts argue the system worked as designed because it detected an anomaly, escalated quickly, and then halted once verification failed. In this view, redundancy prevented catastrophe. The incident is interpreted as a successful stress test. Other historians and strategic analysts argue the opposite. They emphasize that the system moved too far into real alert actions before confirmation. In this view, the incident proves that warning systems can generate crisis behavior from internal error. The fact that safeguards eventually work does not erase the risk created in the interim. This debate is about what counts as success. Is success avoiding nuclear launch? Or is success avoiding unnecessary mobilization in the first place? A second debate concerns adversary visibility. How much did the Soviet Union observe, and how much could it have inferred? The USSR did not see the internal NORAD displays. It could only observe external U.S. behavior. Some analysts argue the alert actions were short and limited enough that Soviet intelligence likely did not detect meaningful changes. Others argue that even small shifts in U.S. communications posture could be noticed by a capable SIGINT system. This matters because the true strategic danger is not only the false alarm, it is the possibility that the false alarm produces observable mobilization. That mobilization can become a signal. A third debate concerns what kind of failure this was. Some interpretations frame it as a technical glitch. Others frame it as an institutional systems failure. The systems failure interpretation is stronger. Because the problem was not random hardware malfunction, it was a pathway in which test/training inputs could enter operational channels. This is a design vulnerability. Design vulnerabilities do not disappear through better training alone. They require architecture change. A fourth debate concerns how the incident should be categorized in Cold War risk history. Some analysts place it alongside later false warning cases, such as the 1983 Soviet early warning incident and other near-miss episodes. Others argue the 1979 event was less dangerous because it was corrected quickly and did not involve actual sensor detection of missiles. Both perspectives are partially correct. The 1979 incident was less close in the physical sense, but it was still dangerous in the systemic sense, because it shows how quickly the U.S. strategic machine could move into alert posture based on internal error. A fifth debate concerns doctrine itself. Launch on warning logic is often defended as necessary for deterrence survivability, but incidents like 1979 highlight the cost. The cost is that early warning systems become decision accelerators. They force institutions to act before certainty. They turn technical ambiguity into strategic motion. This is the key lesson. The incident proves several structural points about Cold War stability. First, nuclear stability was not guaranteed by MAD alone. MAD assumed rational actors and secure second strike forces, but it did not solve the problem of false perception. Second, the nuclear system was vulnerable to internal errors that looked externally meaningful. The most dangerous errors are not ones that stay inside the building. They are ones that generate outward signals, alert levels, communications changes, dispersal actions. Third, early warning systems are designed with asymmetric incentives. They punish missed warnings. They tolerate false alarms. This creates an institutional bias toward mobilization. Fourth, the system depended heavily on redundancy and cross-checking. Redundancy worked here, but it worked under time pressure. That means stability depended on speed and competence at multiple layers simultaneously. Fifth, the incident shows that human judgment is not a substitute for system design. Humans did not prevent the warning. They prevented escalation by applying procedural verification. This is a limited form of safety. Finally, the 1979 NORAD false warning demonstrates the Cold War's most important structural danger. Nuclear crises could be produced by the system itself. Not by political intent, not by strategy, but by the interaction of automated warning, doctrinal time pressure, institutional incentives, real-world mobilization procedures, adversary observation risk. In strategic terms, this incident proves that the late Cold War was not only a contest of weapons, it was a contest of decision-making speed under uncertainty. And that is a fragile basis for stability.